Your body is a nuclear bomb. I want you to look at your hand. Go ahead, look at it. The skin, the knuckles, the small hairs, the veins running just below the surface. It looks ordinary. It looks harmless. It is the same hand you have seen every day of your life. You know this hand. It has never done anything alarming. That hand contains enough nuclear energy to destroy an entire city. Not metaphorically, not in some loose poetic sense where I'm trying to make a philosophical point about human potential. I mean in the precise, quantitative, experimentally confirmed sense of the word. The atoms in your hand, the carbon, the hydrogen, the oxygen, the nitrogen, the calcium, each of those atoms has a nucleus, and locked inside those nuclei, held together by the most powerful force in the known universe, is an amount of energy that would make the bomb dropped on Hiroshima look like a firecracker. The number is not approximate. It is calculated from one of the most precisely confirmed equations in the history of science. An equation written down in 1905 by a 26-year-old patent clerk who had no laboratory, no institution, and no equipment, only mathematics and the courage to follow it wherever it led. E equals mc squared. Your body weighs approximately 70 kilograms. Multiply that by the speed of light squared. What you get is a number so large that no city in the history of the world could survive it. Let me show you exactly why, and exactly why you are still alive. E equals mc squared, what it actually means and why the number is terrifying. Let me start with the equation, because E equals mc squared is perhaps the most famous equation in all of physics, and it is also, with almost no exceptions, the most misunderstood. Most people know the equation as a slogan. They have seen it on t-shirts, on coffee mugs, in newspaper headlines. They know that it has something to do with nuclear energy and nuclear weapons and Albert Einstein. They may know, vaguely, that it relates mass to energy. But the deep meaning of the equation, what it actually says about the nature of matter and energy, what it implies about the material content of your body, what it means that mass and energy are not merely related but are the same thing. This is almost never understood by people who can recite the equation. Let me give you the equation precisely. E equals mc squared. E is energy, measured in joules. M is mass, measured in kilograms. C is the speed of light, approximately 299,792,458 meters per second, a constant of nature, the same in every reference frame, in every laboratory, on every planet in the universe. The equation says that a quantity of mass m is equivalent to is, in a deep physical sense, the same thing as an amount of energy equal to that mass multiplied by the square of the speed of light. Now let us do the arithmetic. The speed of light is approximately 3 times 10 to the 8th power meters per second. The square of the speed of light is approximately 9 times 10 to the 16th power, 90 quadrillion meters squared per second squared. So for every kilogram of mass, the equivalent energy is approximately 9 times 10 to the 16th joules. 1 kilogram, 90 quadrillion joules. For comparison, the atomic bomb detonated over Hiroshima on the 6th of August 1945 released approximately 6 times 10 to the 13th joules, 60 trillion joules. It killed approximately 80,000 people immediately and destroyed approximately 12 square kilometers of the city. 1 kilogram of mass, fully converted to energy, releases approximately 1,500 times more energy than the Hiroshima bomb. Not 1,500 joules more. 1,500 Hiroshima bombs worth more from 1 kilogram. Your body contains approximately 70 kilograms of mass. If the mass energy of your body were fully released, if all 70 kilograms were converted atom by atom from matter to pure energy, the release would be equivalent to approximately 105,000 Hiroshima bombs, not in the same yield class, not in the same order of magnitude. A release of energy so catastrophic that it would not merely destroy a city, it would likely alter the climate of the planet. This is not speculation. This is arithmetic applied to one of the most precisely confirmed equations in the history of experimental physics. The equation E equals mc squared has been verified in nuclear reactors, in particle accelerators, in the decay of radioactive isotopes, in the fusion of hydrogen nuclei in the sun. It is not an approximation. It is not a theoretical idealization. It is a precise description of how the universe actually works. And it says that the mass of your body, the 70 kilograms of matter that constitutes you, is equivalent to an amount of energy that dwarfs every nuclear weapon ever built. Now, before I explain why you are not currently exploding, let me take you deeper into what E equals mc squared actually means. because the equation is more profound than even the Hiroshima comparison suggests. The equation does not say that mass can be converted to energy under special circumstances. It does not say that mass and energy are two different things that happen to be related by a conversion factor. It says something far more radical, that mass is energy. That matter is a form of energy. That the distinction between mass and energy that human beings have made throughout all of history, the intuitive distinction between stuff and the capacity to do things, is not a fundamental distinction. It is an approximate description, valid at low energies, of something that is, at the fundamental level, a single unified quantity. This is what makes the equation revolutionary. Not the number it produces when you calculate it, the conceptual rearrangement it demands. Before 1905, energy and mass were thought to be entirely separate concepts. Energy was something that objects had or exchanged. Mass was something that objects were made of. The two were related. You needed mass to carry kinetic energy. You needed mass in a gravitational field to have potential energy, but they were fundamentally different kinds of things. After 1905, this separation cannot be maintained. Mass and energy are two aspects of a single quantity. When you add energy to a system, when you heat it, or compress it, or charge it, you also increase its mass, because the energy you have added contributes to its mass energy. The effect is unmeasurably small at everyday energies. You cannot weigh the extra mass of a cup of hot tea compared to a cup of cold tea with any scale in any kitchen, but the effect is real. And in the regime of nuclear physics, where the energies involved are millions of times larger than the energies of chemistry, the effect is not only measurable, but the dominant feature of the physics. Let me give you a specific example that makes this concrete. A proton, the positively charged particle in the nucleus of a hydrogen atom, has a mass of approximately 6,726 times 10 to the minus 27 kilograms. A neutron, the electrically neutral particle, also found in atomic nuclei, has a mass of approximately 1.6749 times 10 to the minus 27 kilograms. If you take one proton and one neutron and allow them to combine into a deuteron, the nucleus of deuterium, the heavy isotope of hydrogen, the resulting nucleus, has a mass of approximately 3.3436 times 10 to the minus 27 kilograms. Now, 1.6726 plus 1.6749 equals 3.3475 times 10 to the minus 27 kilograms. But the deuteron's mass is 3.3436. The difference is approximately 0.0039 times 10 to the minus 27 kilograms, a tiny fraction of the combined mass of the proton and neutron. Where did that mass go? It was released as energy when the proton and neutron combined. The binding energy of the deuteron, the energy released by the formation of the nuclear bond, corresponds through E equals mc squared to precisely this missing mass. Mass was not conserved. Mass decreased. Energy was released. The missing mass became the energy of the gamma-ray photon emitted when the proton and neutron combined. This is not an approximation. It has been measured in nuclear physics laboratories to extraordinary precision. The missing mass and the emitted energy are related by exactly E equals mc squared. This is nuclear energy. This is what powers nuclear reactors and what powered the bombs of Hiroshima and Nagasaki. Not a new source of energy, not magic. The conversion of a tiny fraction of the mass of atomic nuclei into energy through the breaking or forming of nuclear bonds, releasing energy in proportion to the mass lost times the square of the speed of light. And the nuclei of the atoms in your body contain this energy, this mass energy, this stored binding energy locked inside their nuclear bonds, waiting in every nucleus of every atom that constitutes you. You are, in every precise and literal sense of the word, made of nuclear energy. But why does none of it release? Why do you not explode? Why is there a human being sitting here reading these words rather than a crater where a human being used to be? The answer is the most powerful force in the universe, and understanding it changes the way you see every atom you have ever touched. The strong nuclear force, the most powerful lock in the universe. The reason you are not currently a nuclear explosion is a force so powerful, so staggeringly intense at close range, that it makes every other force in your daily experience, gravity, friction, the push of your fingers against a keyboard, seem like the gentle suggestion of a calm afternoon. The force is called the strong nuclear force, and it is the thing that holds the nuclei of your atoms together against every reason they should fly apart. Let me explain why atomic nuclei need to be held together at all, An atomic nucleus, with a few exceptions, contains both protons and neutrons. The protons are positively charged. Like charges repel, two protons in close proximity experience an electromagnetic repulsive force that, at nuclear distances at separations of approximately a femtometer, 1/4,000,000th of a meter, is absolutely ferocious. The electromagnetic repulsion between two protons at nuclear separation is approximately 230 newtons. 230 newtons at a distance of a femtometer. Force that, if it could be scaled up to objects of human scale, would be incomprehensible. And yet protons sit happily in nuclei, in close proximity to other protons, without flying apart. The carbon nucleus in your body, the one in your DNA right now, has 6 protons packed together in a sphere approximately 3 femtometers in diameter, all of them experiencing fierce mutual repulsion, and yet the nucleus does not explode. The nucleus is stable. It has been stable for billions of years. It will remain stable for billions more. The reason is the strong nuclear force. The strong force is carried by particles called gluons, and it acts between quarks, the fundamental constituents of protons and neutrons. Each proton and each neutron is made of 3 quarks, and the gluons that bind those quarks together are the carriers of the strongest interaction known in physics. The residual effect of this quark-binding interaction extends slightly beyond the individual proton or neutron, producing an attractive force between neighboring nucleons, between neighboring protons and neutrons, called the nuclear force, or the strong force at the nucleon level. This residual strong force is extraordinarily powerful at close range, at separations of about 1 to 3 femtometers. It is approximately 100 times stronger than the electromagnetic force. This is why it can overwhelm the electromagnetic repulsion between protons and hold the nucleus together. A proton inside a nucleus experiences both the repulsive electromagnetic force from other protons and the attractive strong force from all neighboring nucleons. For nuclei up to a certain size, the strong force wins. The nucleus is stable, but the strong force has a critical property that the electromagnetic force does not. It is short-ranged. The electromagnetic force decreases with the inverse square of the distance it reaches across any distance, however large, however small. The strong force, by contrast, essentially vanishes at distances greater than approximately 2 to 3 femtometers. Beyond this range, the strong force is negligible. This short range has a profound consequence for the stability of large nuclei. In a large nucleus, one containing many protons and neutrons, any given proton is attracted by the strong force only to its nearest neighbors, because beyond a few femtometers, the strong force is negligible. But the same proton experiences electromagnetic repulsion from every other proton in the nucleus, because the electromagnetic force is long-ranged. In a large nucleus, the electromagnetic repulsion from all the distant protons adds up and can begin to overwhelm the short-range strong force. The nucleus becomes less stable. This is why very large nuclei, uranium, plutonium, thorium, are radioactively unstable. In uranium, 235, with 92 protons and 143 neutrons, the electromagnetic repulsion has grown large enough relative to the strong force that the nucleus sits on the edge of stability. A neutron striking the nucleus can provide just enough disturbance to push it over the edge, causing it to break apart, to undergo nuclear fission into 2 smaller nuclei, plus several neutrons, plus a gamma ray. The total mass of the products is less than the mass of the original nucleus plus the incoming neutron. The missing mass has been converted to energy, and the energy is enormous. The 3 neutrons released in the fission can each strike another uranium nucleus and cause another fission, releasing more neutrons, causing more fissions, a chain reaction that, if uncontrolled, proceeds exponentially and releases the energy of millions of individual fission events in a tiny fraction of a second. This is what a nuclear weapon does. Your body does not do this. The carbon, hydrogen, oxygen, and nitrogen atoms that make up the overwhelming majority of your mass have small nuclei. Carbon has 6 protons, oxygen has 8, nitrogen has 7, hydrogen has 1. These small nuclei are deeply stable. The strong force easily overwhelms the electromagnetic repulsion in nuclei this small. There is no mechanism, under ordinary conditions, that can cause these nuclei to undergo fission. No chain reaction is possible. No spontaneous release of nuclear energy occurs. But the mass energy is there. It is locked in the nuclear bonds of every atom. The binding energy of the carbon 1,2 nucleus, the amount of energy that was released when its 6 protons and 6 neutrons were assembled, from their constituent quarks and gluons is approximately 92 MeV, where MeV stands for mega electron volt, a unit of energy used in nuclear physics. 1 MeV is approximately 1.6 times 10 to the minus 13 joules. 92 MeV per carbon, 1,2 nucleus. Your body contains approximately 7 times 10 to the 27th atoms. The total nuclear binding energy, the total energy that would be released if every nuclear bond in every atom in your body were simultaneously dissolved, is staggering in its magnitude. I want to be precise about a distinction here that is important. The nuclear binding energy is not exactly the same as the full mass energy E equals mc squared. The full mass energy includes the rest mass of the quarks themselves, the gluon field energy, the electromagnetic energy of the protons, everything. The nuclear binding energy is the energy associated specifically with the formation of the nucleus from its constituent protons and neutrons, not the deeper energy of the quarks themselves. But this distinction, while important for precision, does not change the fundamental point. At every level of structure, at the level of nuclear bonds, at the level of quark confinement, at the level of the mass energy of the fundamental particles themselves, your body contains an astronomical quantity of energy locked in by forces so powerful that no ordinary process, no temperature, no pressure, no chemical reaction can release more than a negligible fraction of it. The vault is full. The vault door is made of the strongest force in the universe, and you are walking around completely unaware, carrying the equivalent of 100,000 Hiroshima bombs in the atoms of your own body. Now let me tell you where those atoms came from, because the story of how your atoms acquired their nuclear binding energy is one of the most beautiful and most astonishing stories in all of physics. Your atoms were forged in stars, the nuclear history of you. Your atoms were forged in stars. This is not poetry. It is nuclear astrophysics, and it is as precisely understood as any process in science. Every carbon atom in your body, every oxygen atom, every nitrogen atom, every calcium atom in your bones, each of these was produced inside the core of a star that lived and died before the sun was born. The nuclear reactions that forged them, that assembled protons and neutrons into the specific nuclei of the elements, released exactly the binding energy I described in the previous part. And those reactions are happening right now in the cores of every star visible in the night sky. Let me trace the story from the beginning. In the first 3 minutes after the Big Bang, the universe was hot enough temperatures exceeding 1 billion degrees for nuclear fusion to occur. Protons and neutrons combined to form nuclei. The reactions proceeded rapidly, and by the time the universe had cooled below the threshold for nuclear reactions, approximately 3 minutes after the Big Bang, the nuclear composition of the universe was fixed. Approximately 75% hydrogen by mass, approximately 25% helium, and trace amounts of lithium. No carbon, no oxygen, no nitrogen, no calcium, no iron. The Big Bang produced none of these elements. Every element heavier than lithium was produced later, inside stars. A star like our sun is a nuclear fusion reactor of extraordinary scale. At its core, where the temperature reaches approximately 15 million degrees Celsius and the density is approximately 150 times the density of water, protons are moving fast enough to overcome their mutual electromagnetic repulsion and approach each other closely enough for the strong force to engage. When two protons collide at sufficient energy, one of them can convert to a neutron through a process involving the weak nuclear force, emitting a positron and a neutrino, and the proton-neutron pair binds together as a deuteron through the strong force, releasing the binding energy as a gamma-ray photon. The deuteron then captures another proton to form helium, 3, and 2 helium. 3 nuclei combine to form helium, 4 plus 2 protons. The net reaction, called the proton-proton chain, converts 4 hydrogen nuclei into 1 helium, 4 nucleus, releasing approximately 26.7 MeV of energy. The mass of 4 protons is slightly more than the mass of 1 helium, 4 nucleus plus the 2 positrons and 2 neutrinos released. The missing mass, approximately 0.7% of the original mass, is released as energy, 0.7%. That is the mass-to-energy conversion efficiency of hydrogen fusion. It sounds small, but applied to the sun's mass through E equals mc squared, 0.7% of the proton mass represents enough energy to keep the sun burning at its current luminosity for approximately 10 billion years. The sun converts approximately 620 million tons of hydrogen to 616 million tons of helium every second. The 4 million tons of missing mass, 4 million tons per second, is converted to energy and radiated across the solar system. The sunlight that falls on your face is the kinetic energy of photons produced by the conversion of mass to energy in the sun's core 8 minutes ago in nuclear reactions that are structurally identical to the ones described by E equals mc squared. But the sun, a medium mass star, can only fuse hydrogen to helium, and in a later stage of its life, helium to carbon. To build the heavier elements, oxygen, nitrogen, neon, magnesium, silicon, sulfur, all the way up to iron, you need more massive stars with higher core temperatures and higher pressures. And to build the elements heavier than iron, copper, zinc, silver, tin, gold, platinum, uranium, you need the extreme environments of stellar explosions. Massive stars, stars of 8 or more solar masses, live fast and die violently. They burn through their hydrogen in millions of years rather than billions. When the hydrogen is exhausted, the core contracts and heats until helium fusion ignites. When helium is exhausted, carbon fusion ignites, then oxygen, then neon, then silicon. Each successive fuel burns faster than the last, at higher temperatures and higher pressures, releasing the binding energy of progressively more tightly bound nuclei. At each stage, the binding energy released per nucleon per proton or neutron is smaller than at the previous stage, because the curve of nuclear binding energy rises steeply from hydrogen to iron and then falls. Iron 5,6 is the most tightly bound nucleus of all. It has the highest binding energy per nucleon. Fusing iron consumes energy rather than releasing it. The silicon burning stage, which produces iron, is the last stage of stellar nuclear burning that can support the star against gravitational collapse. When the silicon is exhausted and the iron core reaches approximately 1.4 solar masses, the core collapses catastrophically in less than a second. The gravitational potential energy released in this collapse is approximately 3 times 10 to the 46 joules, more energy than the sun will radiate in its entire 10 billion year lifetime, released in a second. Most of this energy is carried away by neutrinos. The outer layers of the star, still falling inward, bounce off the suddenly rigid neutron star surface and are blasted outward at 10,000 kilometers per second, a core collapse supernova. In the extreme conditions of the supernova, the intense neutron flux of the collapsing core, the billion-degree temperatures, the shock wave tearing through the stellar envelope, nuclear reactions occur that are impossible under any other conditions in the universe. The rapid neutron capture process, the R process, builds nuclei heavier than iron by repeatedly capturing neutrons faster than they can decay. This process produces the majority of the heavy elements, the gold in your jewelry, the platinum in your catalytic converter, the uranium in nuclear reactors. And then the supernova blasts all of these elements, the carbon, the oxygen, the nitrogen, the silicon, the iron, the gold, into the interstellar medium. The exploded material mixes with the gas and dust of the galaxy, and over millions of years, gravity assembles some of this enriched material into new molecular clouds, which collapse to form new stars and new planetary systems. Our solar system formed from such a cloud approximately 4.6 billion years ago. The cloud contained hydrogen and helium from the Big Bang, plus carbon, oxygen, nitrogen, silicon, iron, gold, and every other element heavier than lithium, the ashes of one or more generations of massive stars that had lived and died before the sun was born. The Earth, forming from the heavier elements in the solar nebula, contains these stellar ashes, and every living thing on Earth, including you, is built from the same material. The carbon in your DNA, the oxygen in your hemoglobin, the calcium in your bones, every atom was produced in a stellar interior or a stellar explosion, released into the galaxy, and assembled by chemistry and biology into the specific molecular structures of your body. Your atoms carry the history of the universe in their nuclear structure. Every nucleus in your body contains the binding energy deposited in it when it was forged in the core of a star, in a supernova explosion, in the first 3 minutes of the universe. That binding energy, that locked, dormant, astronomical amount of energy, is as old as the atoms themselves, some of which are nearly as old as the universe. You are not just made of nuclear energy. You are made of ancient nuclear energy, produced in the most extreme events in the history of the cosmos, distributed across the galaxy, assembled by the gentle processes of chemistry and biology, and organized into the specific, improbable, extraordinarily complex structure called a human being. The nuclear bomb analogy is not an exaggeration. It is, if anything, an understatement. Because a nuclear bomb is simply a device that releases a fraction of a percent of the mass energy of a small amount of fissile material. Your body contains the mass energy equivalent of 100,000 nuclear bombs in the nuclei of atoms forged in events far more energetic than any nuclear weapon ever produced. But the energy is not yours to use. It belongs to the strong force, and the strong force does not negotiate. Conservation of energy, you are borrowed energy. Returning to the universe, let me bring this all together, because I have told you that your body contains the energy of 100,000 nuclear bombs. I have told you where that energy comes from, the nuclear binding of protons and neutrons, the mass energy equivalence of E equals mc squared. I have told you why it does not release the strong nuclear force holding every nucleus together with a grip that chemistry and biology cannot loosen. But I have not yet told you the deepest thing. The thing that, when I understood it fully, made me stop and sit with it for a long time before I could move on. The deepest thing is this: energy cannot be created or destroyed. This is the first law of thermodynamics, the conservation of energy. And it is not just a rule of thumb, not just a useful approximation, not just a statement that applies in the laboratory and breaks down in some extreme regime. It is, as far as every experiment ever performed in the history of physics can determine, an exact and absolute law of nature. Energy is conserved, always, everywhere, without exception. This means that the energy in your body, the kinetic energy of your moving atoms, the chemical energy of your molecular bonds, the electrical energy of your neural signals, the heat energy of your body temperature, and the nuclear binding energy locked in every nucleus of every atom, none of this energy appeared from nowhere. It was all here before you were. It was in the food you ate and the sunlight that grew that food and the nuclear reactions in the sun that produced that sunlight. It was in the stars that forged your atoms before the sun was born. It was in the Big Bang that created the protons and neutrons that were assembled into those stars. The energy that constitutes you has been here in various forms for 13.8 billion years. You are not a new injection of energy into the universe. You are a temporary organization of energy that has been cycling through the universe since its beginning. And when you die, when the organized structures that constitute you dissolve, when the molecules break apart, when the atoms scatter into the soil and water and air, the energy does not disappear. It goes somewhere else. The chemical energy of your molecular bonds becomes heat as bacteria decompose your tissues. The atoms are incorporated into new molecules, new organisms, new structures. The energy continues its journey through the universe, taking on new forms, new organizations, never created and never destroyed. This is what conservation of energy actually means for a living thing. You are not using energy, you are borrowing it, temporarily organizing it, and returning it to the universe in a different form. The energy was here before you arrived, and it will be here after you leave. You are a transient structure, extraordinarily complex, extraordinarily improbable, extraordinarily beautiful, through which the universe's energy flows for a brief time. Now, there is something I want to address about E equals mc squared that most discussions skip, and that I think is deeply important for understanding what the equation actually says. The equation E equals mc squared, as Einstein first derived it in 1905, was derived for a specific case, a body at rest. What the equation says precisely is that a body at rest, a body with no kinetic energy, no potential energy, no thermal energy, has an intrinsic energy equal to its rest, mass times c squared. This rest energy is the mass energy, the energy stored in the mass of the body itself, in the mass of its constituent particles, and the binding energies of its constituent structures. The full expression for a body that may be moving is E squared equals the quantity pc squared plus mc squared. The whole thing squared, where p is the momentum of the body. For a body at rest, momentum is 0, and this reduces to E equals mc squared. For a massless particle like a photon, m is 0, and E equals pc, the photon carries energy purely through its momentum. This relativistic energy-momentum relation is the correct and complete statement of mass-energy equivalence. It was derived by following the mathematics of special relativity, the principle that the laws of physics are the same in every inertial reference frame, combined with the constancy of the speed of light to its logical conclusion, the conclusion is that mass and energy are the same thing, differing only in form, and that the conversion factor between them is c squared. The implications of this go beyond nuclear physics. The mass of a hydrogen atom is slightly less than the sum of the masses of a proton and an electron, because the bound state has less energy than the separated state. The binding energy of the hydrogen atom is negative, and this negative energy contributes a tiny decrease in mass. The same principle applies to every bound system in nature. A molecule, a crystal, a planet, a galaxy, every bound system has slightly less mass than the sum of its parts, because the binding energy, the energy released in forming the bound state, is carried away when the system forms, taking its mass equivalent with it. This is profound. It means that mass is not a fixed intrinsic property of objects that simply gets added up when objects combine. Mass is a form of energy, and it changes when systems form or dissolve. The mass of a bound system depends on the energy state of the system, not just on the masses of its components. And your body is a bound system, an extraordinarily complex, hierarchically organized, thermodynamically improbable bound system. Your body has a specific mass. That mass is the sum of all the energy forms. It contains the rest masses of all your fundamental particles, the binding energies of all your nuclear structures, the binding energies of all your chemical structures, the kinetic energy of all your molecules divided by c squared. Every change in your energy state, every meal you eat, every joule of heat you radiate, every photon of light that reaches your skin changes your mass by an amount so tiny as to be unmeasurable, but in principle real. You are heavier after eating. You are lighter after you radiate heat. You lose mass when you exhale carbon dioxide. The mass differences are fantastically small, a few micrograms at most, but they are real, predicted by E equals mc squared, confirmed by the same physics that makes nuclear reactors work. Now, let me tell you something that I find most beautiful about all of this. Not the numbers, not the comparison to nuclear weapons, dramatic as that is. The beautiful thing is the unity. E equals mc squared says that mass and energy are not two different things related by a conversion factor. They are the same thing. The apparent distinction, the intuitive sense that matter is stuff and energy is capacity, is an illusion produced by the low energy regime of everyday experience, where the mass equivalent of energy changes is too small to measure. In the true physics of the universe, in the regime where the temperature is high enough that rest mass and kinetic energy are comparable as they were in the early universe, as they are in particle accelerators, there is no meaningful distinction. Particles and energy are interchangeable. Matter is frozen energy. Energy is liquid matter. Your body is frozen energy. The 70 kilograms of matter that constitutes you is 70 kilograms of energy in a particularly organized, particularly stable, particularly temporary form. The form that can move, that can think, that can feel, that can ask questions about the universe it is made from. When you look at your hand and see the skin and the veins and the small hairs, you are looking at energy that has been here since the Big Bang, that passed through generations of stars, that was forged in nuclear fires of unimaginable temperature, that was scattered across the galaxy, that was assembled by the slow chemistry of planetary evolution and the extraordinary improbability of biological evolution into a form that has become, for this brief moment of cosmic time, a human being. And in the nucleus of every atom of that hand, in the tight, dense, unimaginably powerful structure of every proton and neutron, sits the binding energy that makes it matter, that makes it mass, that makes it real in the physical sense, that makes it equivalent through the most famous and most precisely confirmed equation in all of physics to enough energy to dwarf every weapon ever built. You are not walking around safely because you lack energy. You are walking around safely because the force that locks your energy in place is the strongest thing in the universe. And that is, I think, the most extraordinary and most underappreciated fact about the nature of the material world. The world is not made of stuff. It is made of energy in a form so stable, so tightly locked, that it appears to be stuff. Matter is the universe's way of storing energy so effectively that it takes the most extreme conditions, the interiors of stars, the cores of nuclear reactors, the explosive chain reactions of weapons to unlock even a tiny fraction of it. The rest, the overwhelming majority, the 99.9% that the strong force holds with an iron grip that chemistry cannot loosen, sits quietly in your atoms. stable, latent, ancient, waiting. You are a nuclear bomb that will never go off. And that, against all the odds of the universe, is exactly what you need to be.